So this is chapter number 7, water quantity and water quality. Very important chapter. First of all, we have to define the meaning of pollution. What is pollution? It is the introduction of a substance to the environment at a level leading to a loss of beneficial use of water. When the water will not be beneficially used, and of course the same thing for air. There is a loss of beneficial use of air and land resources. Okay, so this is the definition of pollution, or degradation of the health of the humans, wildlife, or ecosystem. Of course, pollutants are discharged to the aquatic system from a point source, either like, let's say that this is a stream, a river, and there's a pipe coming in from the Ministry of Public Works emitting wastewater. This is a point source. So there is two ways that pollutants are discharged to the ecosystem, either through a point source, this is the point source, which is like a stationary location such as an effluent pipe, or from a non-point source. A non-point source, for example, if you see that this is the Arabian Gulf, and all these cars moving in the Arabian Gulf are emitting air pollution, and all this air pollution coming to the atmosphere, going to the atmosphere, and then there's the sea. So all these pollutants coming in as an endpoint, okay, non-point source. We call it sometimes diffusive or diffuse. Such sometimes land runoff is an endpoint source, of course, and the atmosphere. Pollutants can be going to the environment as an endpoint source. The degree of the pollution in water is typically described by units of concentration, or sometimes it's either concentration or the mass flux, or sometimes we call it loading. So this is the unit of mass per unit time. Okay, we have to have some engineered approaches to pollution management that vary with the type of material in question. Pollutants such as nitrogen, phosphorus, organic matter, suspended solids are all discharged to rivers, to lakes, to oceans. And this is of the world by tens of millions of tons per year. Tens of millions of tons per year. Nitrogen, phosphorus, organic matter, and suspended solids. We'll show you the figure in the next slide. That will show the biochemical oxygen demand. Remember the BOD that we talked last lecture. And of course the biochemical oxygen demand loading in megatons per year to a global waterways for agricultural, domestic, and industrial sectors in 1995. You can see that this is the OECD, the Organization for Economic Cooperation and Development. Okay, this is it. And you can see that the megaton per year of BOD, this is to note that there is some large contribution of the agriculture sector to global BOD. Look at this agricultural, how much the large contribution of BOD, while also the non-OECD, the contribution for agriculture is really huge. Okay? We will say it again. What is BOD? BOD is the organic content of the wastewater. And of course, you could note from these two, from this figure A, that there is a large contribution of agricultural sector to global BOD, and of course to nitrogen loadings. This is one of the reasons that the National Academy of Engineering has designated managing the nitrogen cycle as one of the century's grand challenges. So, this is the BOD loading to waterways by sector, either through the OECD or through the non-OECD. And this is the nitrogen loading to waterway from agricultural. And you can see it from the years, and you can see that throughout these years, it was increasing from 1995, 2010, and 2020. Okay, same thing for non-OECD. You can see it 1995, increased to 2020, and a big increase in 2010 and 2020. Okay, do we have enough water in this earth? Well, the total volume of the water of the world water is estimated to be 1.386 10 to the 9 kilometer cube. Okay, that is the total water estimation. The ocean holds 96.5% of this total volume. The atmosphere contains only 1.29 10 to the 4 kilometer cube, as like clouds, as humidity. So it's still huge. It's still huge. But if you compare this to the big one, which is only 0.001% of the total hydrosphere. We'll see the table 7.4 in the next slide, but the total amount of fresh water on our planet is approximately 3.5 10 to the 7 kilometer cube. In terms of this, 3.5 10 to the 7, only 2.5% of the world total water budget is estimated to be fresh water. Only 2.5%. And 70% is currently present as glaciers and ice sheets in the North Pole and South Pole. Okay, so 2.5% is available as fresh water for now. So the table that we're going to show in the next slide, it's table 7.4, gives you which shows a large percentage of the world's fresh water is available as a groundwater resource, much of which has a renewal period of over 1,000 years. So the groundwater is not that easy to renew itself. It takes 1,000 years for the groundwater to refresh or to renew itself. So let's look at the percent of world total fresh water in different locations. The total amount of fresh water on Earth's surface is 3.5 10 to the 7 kilometer cube. You can see the glaciers and permanent snow cover, 68.7%. Groundwater, 30.1. This is very critical. We have to really conserve. Lakes, 0.26. Soil moisture, 0.05. Atmosphere, 0.04%. 0.03 for marshes and swamps. 0.003 for biological water, and rivers, 0.006%. All of this information shows that very little of the total freshwater budget is available as surface water, like lakes or rivers, or as a groundwater that's recharged over a short duration. Now, what is water usage? Of course, water is required by a wide variety of human users, including residential homes, including commercial entities, including industry, including agriculture, and importantly, ecosystems. Water is very important. This concept of ecological footprint that right now most of these researchers are including in their publication assumes that some of the world's ecological capacity should be preserved for biodiversity protection. And this ecological capacity requires, of course, H2O, water. In addition, while everyone in the world depends on ecosystem for their social, economic well-being, much of the world poor, those living on less than $1 or $2 per day, depend even more on ecosystems for their economic livelihood. Of course, we have to do the management of the water that's being distributed among various users because it's a very important parameter to control water usage. Globally, there's 3,800 kilometer cubic of water are withdrawn every year. Of this, is 2,100 kilometer cube are consumed by humans. Consumed water is either evapotranspirated from trees, from grass, or incorporated into products or organisms. The difference of 1,700 kilometer cube, the difference between how much withdrawn and how much is consumed, 1,700 kilometer cube is returned to local water bodies, usually as wastewater. That's coming up from residents, that's coming up from industry. So this 1,700 kilometer cube is going to be as wastewater, coming from domestic and industrial users. This huge volume returned to the local water system may not be available for easy reuse. And it's all of this depending on what? On its next use, and importantly, whether it has been contaminated or treated prior to the charge. Of course, this wastewater has to be treated probably before you discharge it to the waterway or before you use it for irrigation. So what is a water footprint? The water footprint determines the water required to support human activities. Of course, each country are responsible for half of the world water footprint. You can see it right now in order of consumptions. So these 8 countries, the 8 countries that are responsible for half of the world water footprint, India has the highest water footprint. Next, China has the second highest water footprint. United States of America is the third country that has the highest water footprint. Russia, Indonesia, Nigeria, Brazil, and Pakistan. So this is the list of the consumption, the water footprint in order of consumption. On a per capita basis, per capita means per human, for 1997 to 2001, the United States had the highest footprint, 2,483 meter cubic per capita per year, which means that in the United States, the consumption was 2,483 meter cube per human, they say per person, per year. Okay? So if you want to find out how many, what is the volume of the water usage, you should multiply it by the population of the US, 360 million. Person, so person cancel with person, and you should do it, if you want to do it per year, or per 2 years, or per 3 years, whatever. So let's do it per 1 year. So 1 year cancel with 1 year. So you could find out how much water usage per year in meter cubic. In comparison, for the same period from 1997 to 2001, the global water footprint was 1,243 meter cubic per capita per year. This is the global, while the US per capita basis was 2,483, almost 1,000 more than the global water footprint. Footprint of other countries in meter cubic per capita per year are Australia, 1,393, Brazil is 1,381, China is 702, Germany is 1,545, India is 980, and South Africa is 931. Why? You can see it here. India was the number 1 world water footprint. Here it's number 1 is America, 2, 3, 4, 5, 6. It's because of the population of India. Same thing for China. China was number 2, but still China is 1, 2, 3, 4, 5. Number 5 because of the population of China. When you divide by the population, you're going to get a smaller number. The US has less population than China and India. Okay. In this table, you will see the percent of annual water withdrawal associated with agricultural, industrial, and domestic sectors. So you could differentiate between agricultural percent, industry percent, domestic percent. You can see the word 70% of the water goes to the agricultural, 20% to industry, and 10% domestic. Look at North America. And you should compare North America with Latin America. You can see that in North America, 39% is going to the agricultural. While in Latin America and Caribbean, 73% of the water going to the agriculture, which means that here that they depend more in agricultural reuse of the water. While for the industry, 47% of their water use is going to the industry, while 9% of the water use is going for the industry here for Latin America and Caribbeans. Same thing for domestic. You can see it's not that far, 13 to 18%. And you can differentiate the rest between Europe and Africa and West Asia and Asia and Pacific. You could differentiate between which one of them is using more water for agricultural and which one of them is using more water for industry and domestic. So now in this table, you can see that the total freshwater and saline water withdrawal in the United States. And you can see that these withdrawals total is 408 million gallon per day. This is gallon per day, million gallon per day. Freshwater account for 85% of this total, and surface water account for 79% of the total. You can see that these are the users: thermoelectric. This is 48% of the total fresh and saline water withdrawals. Irrigation, public supply, industrial, domestic less than one, livestock, agriculture, and mining. And you can see, of course, here the groundwater and the surface water and the total and the population. You can see that the population has really a greater effect on this increase. You can see that the population increased with time from 1950 to 2000. You can see population is increasing while there was an increasing withdrawal of groundwater, surface water, and this is in what? In billions of gallons per day. Okay? And the total, this is the total of ground and surface water together. You can see there's an increase from here to here to here, all the way up. It's going up. Mostly it's going up. Until you come to year 1985, and they're starting to do some techniques to reduce and to conserve water usage. And you can see that since then, everything is conserved. We'll be talking about these methods in a few seconds. This table shows the sources of water and issues associated with the source, surface water. Like, of course, the issues as high flows, easy to contaminate, and relatively high suspended solids, of course, TSS, and turbidity, pathogens. In some parts of the world, rivers and streams dry up during the dry season. So this is a very important source of water. Groundwater. What are the issues that comes with groundwater? Of course, lower flows, because the flow rate here is high. Here the flow is really low. But neutral filtering capacity that removes suspended, of course, the groundwater has some natural filtering capacity that removes suspended solids, TSS, turbidity, pathogens. In groundwater, you might have some dissolved solids, which is given as total dissolved solid, TDS, including Fe, Mn, Ca, and Mg, and that is for hardness. Of course, it's very difficult to clean groundwater after contamination. Renewal time can be very long. Renewal time can be thousands and thousands of years. Of course, seawater. There's a lot of issues with seawater. It's energy intensive to desalinate, especially that if you want to take the water out of the seawater and desalinate, it is an energy intensive process. It's costly compared with other sources. disposal of resulting brine must be considered. Of course, when you do it here in Kuwait, they do the boiling. Okay, so they boil the seawater and the salt will stay at the bottom, and all this water will be evaporated to the next tank and then condensed to have fresh water without salt. While this brine, the high salty water that stayed after boiling, they were dumped to the sea. So this is what we call it brine. That must be. This is a very big issue that right now they are disposing to the seawater, and this issue has to be discussed and evaluated. Of course, desalination can occur by distillations. Sometimes they call it distillation. Sometimes they use reverse osmosis, RO. And sometimes they use electrodialysis, ion exchange. Of these, multi-stage distillation and reverse osmosis are the two technologies most commonly used. Of course, they account for 87% of the worldwide desalination capacity. Okay, and that's why we use some of the industrial here in Kuwait. They use multi-stage distillation, and some they use reverse osmosis, RO. There are more reverse osmosis plants in the world now. However, they are typically smaller in capacity than distillation system. The last source of water is reclaimed and reused. If you have wastewater and you do treatment, you should reclaim this water, treat it, and then send it for reuse. This is technically feasible, of course. Currently used for irrigation or irrigating agricultural crops, residential and commercial landscaping, okay, for grass, groundwater recharge, and potable water through direct or indirect use, which include decentralized use of grey water, wastewater produced from bath and showers, clothes and dishwasher and lavatory sinks and drinking water fountains. When used for irrigation, nutrients present in reclaimed water can reduce fertilizer usage. In this figure 7.11, which shows the public supply water withdrawal in the United States in 2000, the states and the territories, you can see the total withdrawal in million gallon per day. And if you go from the west to the east, okay, you can see that California has 6,000 million gallon per day usage. Okay, California has huge usage. Okay, you can see Texas has the second state that usage 4,000 almost. This is like 6,000 million gallon per day. This is 4,000 million gallon per day. While the next one is Florida. Okay, Florida has almost 2,500 million gallon per day. Next, or maybe similar to it, New York. Well, if you just look, simply the same thing, 2,500 million gallon per day. So you can see the state from the west to the east, and you can see that the west has more usage of withdrawal of water supply. Now, water usage in the U.S. household. What are the typical and efficient alternatives? Of course, typical water usage in the U.S. household is far greater than when a water efficient fixtures are installed, and a household pay attention to leak detection. Percentages are based on a total use. Let's look at showers in the U.S. When there's a typical water use, look at this, 11.6 gallon per day per capita, or gallon per capita per day. 16.8% going to showers. You can see which one is the highest. Okay, it is toilets, 18.5 gallon per capita per day, 26.7. And the next, clothes washing. Most of the water going to the clothes washing, 15 per gallon per capita per day, 21.7%. the problem here, look at this, leaks 9.5 gallon per capita per day. Of course, every house will have a leak, especially if the pipes are really old, 13.7%. And faucets, of course, 10.9 gallon per capita per day, 15.7%. Now, the total is 69.3 gallon per capita per day. Water uses, if you are using water efficient fixtures and leak detections. Now, of course, this is more expensive, but in some states in the US, they force people, especially if you have a rental property, they will not give you the permit until you have these water efficient fixtures and leak detection systems. Let's look how much reduction. Showers, 11.6 gallon per capita per day. When you have fixtures and leak detection system is 8.8 gallon per capita per day. Let's look at the highest. Which one is the highest now? 18.5 for toilets, 8.2 when you have water efficient fixtures. Let's look at the total, 69.3 if you don't use water efficient fixtures and leak detection system. But when you do this, how much save? You're going to use only 45.3 gallon per capita per day. Okay? So if you are saying this is 70, 45, 25 gallon per capita per day. That's huge. Of course, there's other states like California, Arizona, Georgia, and Florida already incorporate water reclamation and reuse in the water management decisions. Of course, everything is going through reclamation plant, wastewater treatment, and they do reuse into irrigation for agricultural use. Why these states doing this? Because of the weather. It's like the weather here in Kuwait. California, Arizona, and Georgia, and Florida, they have the same hot weather. Of course, they're doing this because their climate and the population is really expanding, huge number of people, and extensive water dependent for agricultural production. Everybody know that about Florida oranges. With this water scarcity now becoming a common occurrence, areas that are or were once thought to be water rich should also consider incorporating water reuse and reclamations into water management decisions. There's some examples of water reclamation and reuse in the US, and all of these sources of reclaimed water are treated as domestic wastewater. On a global scale, water reuse capacity is expected to increase from 19.4 to 54.5 million meter cube per day by 2015. Let's look at this location. Hampton Roads, Sanitation District, Virginia. Okay? The service water and boiler feed water at oil refinery. So use all this reclaimed water for this used. There are some issues here. In this location, they need to treat ammonia during cold weather and produce water with more consistent turbidity levels. So these are some issues that this reclamation plant has to take care of. Let's look at San Antonio water system in Texas. The water comes from this plant, is used for the power plant cooling water, industrial cooling, and river maintenance and landscape irrigation. Well, for this San Antonio water system reclamation plant, the water quality deterioration in distribution system can occur from higher solids content of reclaimed water, concerns of cross-connection with potable water, and impact of high TDS levels on vegetation. So there's some issues with this plant. And you can see that locations for the plant and why they are using these water after reclamation and where and what are the issues. So this is the list. You could just look at this example table of some examples of water reclamation and reuse. Well, are we going to have some conflict in the future for water use? Yes. Water is really short. We need to get some more possibility of getting water some other locations. Are we going to have conflict? I think so. So one of the most pressing global security problems in the future is likely to be water scarcity, which is a situation where there is insufficient water to satisfy normal human requirements. A country is defined as experiencing water stress when annual water supplies drop to below 1,700 meter cubic per person. When the water for the annual, of course, this is, when I say annual, I mean 1,700 meter cube per capita or per person per year. If it went below this, now we can see that this water is experiencing a water stress, or this country. When the annual water supplies drop below 1,000 meter cube per person, the country is defined as a water scarce. By one measure, nearly 2 billion people is currently suffer from severe water scarcity. This number is expected to increase substantially as population increases and as standards of living, and of course, therefore, consumptions rise around the world. This is an example of possible impact of climate change on water resources projected for the mid to late century. Of course, you can see the phenomena and direction of trend, likelihood of future trend based on projections for 21st century, and major impact. Let's look at this. Warm spells, heat waves, frequency increases over most of the land areas. That's the likelihood of future trend is very likely. Major impact, increased water demand. Water quality problems, for example, algae blooms. Let's see. Heavy precipitation events, too much rainfall, frequency increases over most areas, very unlikely over the 21st century. And what are the major impact? Adverse effect on quality of surface water and groundwater, contamination of water supply, water scarcity may be relieved. What other phenomena, like increase in area affected by drought? Okay, this is likely, which will give you more widespread water stress. Increase in intense tropical cyclone activity, likely. Power outage, causing disruption of public water supply. Increased incidence of extreme high sea levels, exclude tsunamis, that's likely. And which the major impact is decreased freshwater availability due to saltwater intrusions. And of course, one of the other phenomena that we just missed here is over most land areas, warmer and fewer cold days and nights, warmer and more frequent hot days and nights, virtually certain because of the global warming. And the major concern here is effects on water resources relying on snow melt, an effect on some water supplies. Okay. This shows the water cooperation or water conflict. Shown are percent of events that have either caused water conflicts or lead to water cooperation. You can see here where the conflict events were cooperative events. Water quantity, the percent, 60%. Well, if it's cooperative, it could go to 35% water quantity. Now we go to infrastructure, dams, canals, etc. It goes from 60 to 85. Well, infrastructure, dams, canals, and extra, it could goes from 35 to almost 55, 20. So this more reduction. Water quality, very small compared to cooperative events. Hydropower, only when they are cooperative events. Okay? And conflict events, joint management and cooperative event, and then the rest as others. Let's look at this example, which will come in the exam as a multiple choice example. You should look at this example. You are working on a project to put in a new set of townhouse apartments. Estimate the daily and yearly water demand. Of course, we will design the pipe based on the daily and yearly water demand. Given that there is 30 apartment units with the average of 3 people living on each unit. So there's 30 apartment units in this building, townhouse buildings, and the average 3 people living in each unit. The typical water usage flow value for this apartment is 100 gallon per person per day. So from these, we will try to find out, we'll estimate the daily and yearly water demand. Okay, let's do the daily water demand. We have 30 units, multiply by 3 people per unit, 3 people per unit, of course, unit is cancelled with units. And now you have people, so 3 times 30 is 90. Times the consumptions, 100 gallon per person per day. And this is person with people. You'll end up with what? 9,000 gallon per day. Okay? Now this is the daily. Yearly water demand is by multiplying the 9,000 gallon per day. You convert the day to a year. So day to year, 1 year is equal to 365 days. So day with day, you'll end up with 3,285,000 gallon per year. Okay, so this apartment buildings will consume 9,000 gallon per day and 3,285,000 gallon per year. We'll stop at this point. And